the outset, let me thank the organizers for having invited me here for this wonderful conference. And we're so well organized and working like clockwork precision. Okay, so today I'll be talking about this interesting compound, which is cobalt doped cerium ruthenium 2 germanium 2. And I would like to show how spin and valence fluctuations drive the quantum criticality in the system. So this basically happens to be the PhD work of my student Swati Pandey, who was earlier at IIT Kanpur as a postdoc and now an NPDF at IIT Indore. And further, we have collaborators from UGC DA CSR Indore Center, Rajiv Rawat, Ramjan Chowdhury, Ashish Mishra, and Sarvanan. And also we have people from BRC, Dr. Yadav, Jha, Bhattacharya, and Pavitra Biswas was also a collaborator. Unfortunately, he is no longer with us. He left us in 22, and incidentally, he happens to be an alumnus of this university also. And of course, the ISS India Nano Mission for providing support for doing measurements at RAR. Okay, so the plan of the talk is roughly talk a little bit about UGC-DA CSR, my earlier institution, and then a brief introduction to quantum phase transitions. Already several speakers have talked about this, and then the non-Fermi liquid behavior and the CET2X2 system, and then in particular the cobalt doped CRU2GE2 system, where we see the role of competing valence and spin fluctuations as a possible origin for the quantum critical point. See, cerium systems have always provided a fertile ground for both theoreticians as well as experimentalists. Again, the main reason being their exotic quantum behavior, which arises from the shifting valence of cerium from 3 plus to 4 plus. Okay, so this is my present affiliation, and I'm thankful to them for providing me support to come all the way here, and so it was nice of them. Then, of course, some of you may not know about this UGC-DA consortium. Well, UGC is University Grants Commission, and DA, as everyone knows. So these two combined together to form this institution and to promote and encourage and support the research using large-scale facilities available at all these big DAE centers among universities and other research institutes. And through this, we facilitate access to the neutron beam facilities at the Dhruva reactor BRC, and Indus synchrotron at Indore, and the cyclotron at VCC Kolkata, and now we also have a center at IGCAR giving access to the low energy accelerators. And at all these centers, we have set up also very high-end research facilities, again for utilization by the university scientists. And one hallmark is that all these facilities are provided free of charge for the scientists. And not only that, we also sometimes try to handhold the scientists right from the stage of proposal writing up to the writing of the manuscript. So we hope that this whole process adds value to the research carried out in our universities and help sometimes in realization of some novel scientific ideas. So this is the Mumbai Center where we have this Dhruva reactor and the neutron beam facility here. So you see this host of neutron spectrometers which have been built by BRC, and we have contributed in our small way by establishing a high resolution powder diffractometer, neutron powder diffractometer with certain special sample environment at the Dhruva reactor. So this is the diffractometer that has been set up by our institute, UGC-DA CSR, and if you look at the instrument parameters, for the first time, of course, we have used a monochromator, which is a bent perfect crystal, which utilizes the principle of momentum focusing rather than real space focusing. And then we have a large flexibility in the wavelengths that can be used. And then most importantly, the delta D by D, or the resolution, is order of about 0.3% over a wide angular range. And to tell you how good this is, I'll just show you a comparison between the same sample which has been run on 2 centers, one at our system on the PD3 as it is called, and then the same sample was also run at the high resolution powder diffractometer at the Paul Scherrer Institute in Switzerland, and you can see that over a fairly large Q range of about 7.5 angstrom inverse, our pattern matches very well with the pattern at the HRPT. So, those of you who are interested in utilizing the spectrometer, they can contact the current instrument scientist, Dr. Somnath Kaushik. He is here. You can raise your hand if you want. Okay, so you can contact him. He is also product of this university, and you can always contact him for any further neutron diffraction experiments. Okay, so now what are quantum phase transitions? Again, my job has been made quite easy by the excellent speakers yesterday and today, and but then just for the sake of completion, yeah. So we always compare this with respect to the classical phase transitions, which basically occur, which are thermal transitions, occur on variation of temperature, and where you will see the order is basically destroyed by thermal fluctuations, and where the control parameter is the temperature over there. And these transitions can be either continuous or discontinuous. But whereas the quantum phase transitions, as you know, they are the t equal to 0 phase transitions, and they are rather driven by quantum fluctuations rather than thermal fluctuations. And now here the control parameter basically drives the phase transition along 0 temperature axis from an ordered ground state to a disordered state at the quantum critical point. And then this control parameter happens to be something like a non-thermal control parameter, like chemical composition, concentration, or magnetic field, or sometimes even pressure. Now, the behavior of this quantum critical system in this quantum critical region is still governed by just above the QCP is governed by quantum critical fluctuations. And now, how do you experimentally access the signatures of this quantum criticality? Basically, you look at certain power laws of the thermodynamic variables, and then you end up in certain non-trivial experiments. So, for example, the non-Fermi liquid behavior, as you all know, is basically it manifests itself as a deviation from the usual Fermi liquid behavior, where the resistivity goes as T square, or the specific C by T is a constant, as well as the magnetic susceptibility. Now, if you look at the cerium atom and look at the environment around the cerium atom, you can see that the 4f shell is quite unstable, and this leads to a strong hybridization between the 4f electron states and the conduction electron states, which gives rise to very interesting properties. And then also the presence of this RKKY interactions, which basically favor the magnetic order, and the Kondo effect, which favors non-magnetic paramagnetic Fermi liquid ground state. They make these cerium as well as even sometimes ytterbium compounds very interesting, because the competition between these two interactions can give rise to quantum phase transition. And of course, it was Doniak way back in 77 who proposed this heuristic description, where we said that the magnetic order and temperature would pass through a maximum and then tends to 0 via second order phase transition at a critical point. And then the Kondo necklace model is well known, where the JCF is the exchange integral between the 4f localized movements and the conduction electrons. And when you have this for small values of GF, we have a magnetic ground state defined by the TRKKY, which goes as J square, and then for the Kondo it goes as an exponential of 1 over JCF, resulting in a non-magnetic ground state for large values of JCF. And so this is a very typical Doniak curve for cerium compounds. So then you can see that as some critical value of J reach again via some non-thermal parameter, you can have a quantum critical point. So now coming to the C T2X2 compounds, where T happens to be a transition metal atom and X is either silicon or germanium, and then these compounds basically crystallize in the tetragonal symmetry with these centrosymmetric I4 by MM space group usually, and then the ground state, magnetic ground state is usually antiferromagnetic. And then by varying the transition metal T in these compounds, can see a variety of ground states. Basically, resulting from a variation in the strength of JCF. So, for example, for CCU2Si2, you can see that it is a heavy fermion superconductor, and the nickel counterpart you have a valence fluctuation state, and CRU2Si2 is a heavy fermion ground state. However, if you see in contrast, CRU2Gu2 is a very unique system where you have actually a ferromatic ground state. Of course, it goes to the ferromatic ground state through an antiferromatic state earlier. And on the other side, we have C cobalt-2 Gu2, which is a heavy fermion intermediate valence fluctuating system. Now, so you can see in CRU2Gu2 as a function of pressure, it goes through a quantum critical point around 6.7 GPa, and and of course it has again several magnetic phases. Number 1 is a ferromatic phase, when 2 and 3 are antiferromatic phases, and then after the quantum critical point it goes into ferroliquid state. But as a function of doping, where you dope iron in place of ruthenium, that also shows a quantum critical point here around at x equal to 0.9. Now, coming to the present work, we have doped cobalt in CRU2Gu2, where see again as I said, CRU2Gu2 is a system where we have a ferromatic ground state, and then you see that for the ruthenium rich side of the composition, we have for x less than 1 RKKY interactions dominate, while for the cobalt rich system greater than x greater than 1.5, we have the Kondo interactions. And then this crossover basically leads to a valence fluctuating state for around the critical composition of around 1.5. And then this basically results from very strong 4f conduction electron hybridization due to a change in the unit cell volume from doping. So, as usual, of course, we went through the characterization, and usually people do XRD, but we happen to do neutron diffraction and everything is fine. Now, if you look at the susceptibility and specific heat data, this is about 2 Kelvin. We see that there are 2 transitions. First, you have antiferromatic phase transition, then goes down into a ferromatic transition, and then at x equal to 1, we are left with mostly the antiferromatic one, a broad transition here. And if you go on increasing x further down, further up, we see a logarithmic behavior for susceptibility here, and as well as for specific heat also. And this is easily apparent here, where for the composition of x equal to 1.5, we see logarithmic dependence as well as power law dependence of this kind with a lambda of 0.71, which suggests non-Fermi liquid behavior. And we also see in the case of specific heat, an external magnetic field actually suppresses this negative logarithmic divergence, and then it crosses over again from a non-Fermi liquid state to a Fermi liquid behavior under magnetic field. Again, with resistivity also we have a similar can I have some water? With resistivity also we have a similar system. Thank you. Where at x equal to 1.5, we have an exponent given by 0.5, which is deviates from n equal to 2 at 0 Tesla, again suggests the deviation from conventional Fermi liquid behavior. However, when we do the resistivity under field, we see that the exponent recovers up to 1.5 under 8 Tesla, which points to recovery of Fermi liquid state. Then the second phase of the experiments we did below 2 Kelvin, but first before that, of course, we undertook CL3H Xane's experiment to determine the rare earth valency, And we also did some X-ray photoelectron spectroscopy of the 3D C3D core level for getting some information on the 4F level configuration as well as the hybridization. And then we did the heat capacity measurements down to 160 millikelvin in different magnetic fields up to 16 Tesla for X equal to 1.5 composition. And then we also did muon spin relaxation experiments measurements down to 50 millikelvin in the both zero field mode as well as the longitudinal field mode for X equal to 1.5. So now the Xain's data basically shows that there is a very strong absorption peak around 5726 eV, and then also there is a prominent shoulder at 5735 eV, which is nearly similar to the CO2 position. So these two basically belong to the 4F1 and 4F0 configurations, and then this flat shoulder which you see here actually it shows that the localized nature of the C3 plus ion, and then the Xain's for both 1.5 and 2 concentrations down to 12 Kelvin clearly show the survival of the 4F0 state down to 12 K. And then we see that there is a gradual increase of C valence with decreasing temperature, and that can be basically explained by the electronic structure change at Fermi level because of the lattice compression and the increase in this 4F and conduction electron hybridization. And then the valence which has been determined through Xain's matches fairly well with the susceptibility measurement. We also did XPS, and you can see that there is a pronounced F2 peak here, so which indicates that there is a remarkable hybridization between 4F and conduction electron states. And then the valence turns out to be around 3.06 at room temperature. Now looking at the specific data down to 160 millikelvin to get a proper insight into low temperature behavior of the critical concentration, we see that basically the C by T as a function of the semi-logarithmic scale, if you see here, it does not show any magnetic ordering down to lowest temperature, and also follows a minus LNT behavior for almost a decade between 0.5 Kelvin to 4 Kelvin, which is again consistent with non-Fermi liquid behavior near a quantum critical point. Then again it is quite interesting to see the data below 0.5 Kelvin where this curve deviates from the logarithmic behavior, and then it is described by a power law of this kind, which is actually in complete agreement with the spin fluctuation model of Moria for the 3D AFM case. Well, this I think our two speakers earlier yesterday have done a very good job of explaining what is muon spin relaxation, etc. I won't go through this, but this is the system which we worked on at ISIS RAL, an excellent system. And basically again, as I said, zero field mu-SR is a very sensitive method for detecting very weak internal magnetic order, and this is just an example of Herbert-Smithite. I think this also was shown yesterday, and you can see as a function of concentration of between zinc and copper, you can see that here you have these oscillations which signify a magnetic order, but whereas here you can see that there is no magnetic order. So when you consider our system, we did the zero field mu-SR measurements first, and then this is what is called the ZF mu-SR asymmetry time spectra at some temperatures from 50 millikelvin to 16 Kelvin, and you don't see any oscillations here or any fast relaxations. So that discards the presence of any static magnetic ordering down to 50 millikelvin. So now when you fit this data using a very well known function Gz, where the GKT is also called the Gaussian Kubo-Toyabe function, results from a Gaussian distribution of these local magnetic fields. You can see here that below 6 Kelvin it follows a power law of with an exponent of 0.36, and then again there is a cutoff at around 200 millikelvin, and then at this point we see that there is a slight degeneracy in the kinds of fit we can do. It can be fitted with 0.3 or 0.5, which signifies a valence fluctuation QCP, and it can also be fitted with, of course, 0.25, which signifies AFM QCP. We also carried out longitudinal field muSAR spectra, and here again with the application of a magnetic field of 11 millitesla, this muon relaxation is quite suppressed and it becomes quite flat. Now, to determine the quantum criticality, you see it is known that all data points of susceptibility, resistivity, and specific they should collapse into a single universal scaling curves up to a certain scale, and these scaling curves characterize the quantum critical points. And here for magnetization, for x equal to 1.5, we can see the existence of the QCP is confirmed by scaling analysis of magnetization as well as resistivity here, and for magnetization the exponent is roughly out of 1.05, and for resistivity also not here. Okay, so basically data sets collapse out to a single curve up to 30 Kelvin and evidencing non-Fermi liquid behavior. And for heat capacity also, the temperature field scaling with this equation gives a beta of 1.1, and for muSAR time field scaling also gives you a gamma of 0.9. So basically the interplay of valence and spin fluctuations, we see that the Xanes has given a valence fluctuating state for x equal to greater than 1.5, and then the existence of AFM QCP is strongly supported by lack of magnetic ordering at 1.5 and confirmed by the ZF muSAR data and heat capacity measurements, and the temperature field time field scaling analysis of both heat capacity as well as longitudinal field muSAR data confirm the significance of critical and cooperative spin fluctuations around this quantum critical point. And then the behavior of lambda ZF very strongly suggested that the role of valence fluctuations persisting down to the lowest measured temperature, and this substantial hybridization of 4F and conduction electrons suggests that there is a simultaneous interplay of spin and valence fluctuations driving the quantum criticality in this system. So this is the final phase diagram which we have with this quantum critical point at around concentration of 1.5. So this is what is the final result of our all studies, and that's the summary. Thank you.
Just a nice question I have. Instead of this critical point, if non-Fermi liquid is in phase, is it really possible to calculate the scattering rate experimentally, which is inversely connected to the imaginary part of the self energy? So is it really possible experimentally to measure?
See, what we do measure is, of course, we depend on the scaling and the exponents that we get from that. So from the exponents we can only theorize, okay, because as compared to the earlier studies on cerium and even ytterbium systems, that these exponents are matching fairly well, and so that's what it is. Thank you.